All right, so let's try to solve these problems based upon the conservative forces and potential energy. So see this problem. The potential energy of a system increases if work is done, and options are upon the system by a non-conservative force, by the system against a conservative force, by the system against a non-conservative force, upon the system by a conservative force. What's the answer? Can you guess? The potential energy increases if work is done against the conservative force or by the conservative force.
Against the conservative force.
Against the conservative force. Very good. So where is against the conservative force? Option B. Option B is the answer. Right? It's simple. Very simple question. So this is from NEET 2011. Okay. Next question. If W1, W2 and W3 are work done in moving a particle from A to B. Okay, so you are moving a particle from A to B along three different paths, 1, 2 and 3 respectively, as shown in the gravitational field of a point mass m. The relation between W1, W2 and W3 is, what is the relation? So this is exactly what we saw yesterday. This is exactly what we proved yesterday. Work done against the gravitational force or work done by the gravitational force. Does it depend on the path or it does not depend on the path? Sorry. Does it depend on
Independent of
path?
the path.
It is independent of the path. So what's the answer? Option B is the answer. Right?
Yes, sir.
Okay, clear everybody? Yes, Ravindran? Okay, good. Next question. The slope of potential, I'm sorry. Okay. So the slope of potential energy versus position graph gives the magnitude of. So what is slope of potential energy versus position? It is derivative of potential energy versus position. It gives the magnitude of what? So we know that conservative force is given by minus of du by dx, right? So if you have,
Rate of change of momentum.
very good. Okay. So it gives you force. That means it gives you what? The rate of change of momentum. Because according to Newton's second law, what is force? It is equal to rate of change of momentum with respect to time. Okay. So the answer is option C. Yes, everybody?
Yes, sir.
Okay, Ravindran. Okay, good. Sorry. Next question. So this is from NEET 2012. The potential energy of a particle in a force field is U equals to A divided by R square minus B divided by R, where A and B are positive constants and R is distance of particle from the center of the field. Okay. For stable equilibrium, the distance of particle is. So what happens at this stable equilibrium? Du by dr will be equal to 0. right? So this can be written as d by dr, or I will write this as a multiplied by r raised to minus 2, okay, minus b multiplied by r raised to minus 1. So this is equal to 0. Fine. What I have done is I have taken this r raised to 2 in numerator, so it becomes r raised to minus 2. So r raised to 1, r means r raised to 1. In numerator, it will become r raised to minus 1. Now let's take derivatives. So if you take derivatives, what will you get? So derivative of this using the formula, derivative of r raised to n. It is n r raised to n minus 1. So this is r raised to minus 2. That means you will have minus 2 multiplied by r raised to minus 3. Okay, this is derivative of this term. A is constant. Okay, minus b multiplied by minus 1 multiplied by r raised to minus 1, that's minus 2. Okay, so here n is minus 1. Okay, and you have, when you take derivative, it becomes n minus 1. So minus 1, it is minus 2. Here n is minus 2, minus 2 minus 1 is minus 3, right? So this can be written as what? So you can write this as minus 2a divided by r cube, okay, and this minus minus becomes plus, plus b divided by r raised to 2. This is equal to 0. You can take r raised to 2 common, okay, divide both of these terms by r raised to 2 and take that 2a on the other side, 2a upon r. So here if you divide by r raised to 2, you will have r here, right? So it is 2a upon r equals to b, or r equals to what? 2a divided by b. Okay, so you have this point at which the derivative of potential with respect to the derivative of potential energy with respect to r is 0. That means you will have equilibrium at this point. Okay, that means force will be equal to 0. So which is the answer? Option B is the answer. So let us see next question. Next question is similar, but it is way back from 1995. The potential energy between two atoms in a molecule is given by U of x equals to this thing, okay, where A and B are positive constants and x is distance between the atoms. The atom is in stable equilibrium when, okay, so let's take derivative again. So for stable equilibrium, du by dx is equal to 0, and now it is d by du of what? This thing, a divided by x raised to 12 minus b divided by x raised to 6. Okay, so shall I take the derivatives directly now? Okay, so if you take the derivative, it will become minus 12. Okay, if you take this in numerator, it is x raised to minus 12. If you take its derivative, it is minus 12 multiplied by x raised to minus 13. That is minus 12 divided by x raised to 13. Right, that's what I am writing. So minus 12 a divided by x raised to 13, and here it will be minus 6, okay, minus 6b divided by x raised to 7, right? And this is equal to 0. So then this becomes minus minus becomes plus. I'm sorry. So you have what? Divide these two terms by x raised to 7. So you have minus 12a upon x raised to 7. Okay. I'm sorry. So what I can do is I can divide these two terms by x raised to 7. What will be this thing then? It will be x raised to 6, right? And then you can divide these two by 6 also. Okay, so this becomes minus 2a upon x raised to 6, okay, plus b upon 1 equals to 0. right? Or you can say this is equal to 2a upon x raised to 6 is equal to b, or x raised to 6 is equal to 2a divided by b. Okay, and this gives you x is equal to 2a upon b raised to 1 by 6. Okay, right? You take sixth root on these both sides because you have x raised to 6. So this is the answer, 2a upon b raised to 1 by 6. Option A is the answer. So clear? Yes, no?
Clear, sir.
Yes, sir.
Good. Okay, so all these questions are simple, right? Next question. A particle with total energy E is moving in a potential energy region U of x. Motion of the particle is restricted to the region when? Okay, U of x is less than E, U of x is less than or equal to E, U of x is equal to 0, U of x is greater than E. So can you tell me what's the answer? We know law of conservation of energy, yes, no? Sum of potential energy plus kinetic energy is total energy.
Yes, sir.
Okay, so we can say U of x plus some kinetic energy half mv square is equal to the total energy, right? And this half of mv square kinetic energy will have some positive value, right? It will have some positive value. So if this is positive, okay, if this is positive, so you have to add something to u of x to get energy E, right? At least how much can be the kinetic energy? The minimum value of the kinetic energy will be equal to 0. Okay, so since you have to add something to the potential energy to get the total energy, that means potential energy is less than total energy, right? At the most it can be equal to the total energy. When it will be equal? When v is equal to 0. V meaning the velocity is equal to 0, right? So u of x is less than or equal to the total energy. Option C is the answer. Okay, potential energy of a particle, they are saying it's proportional to, it's not alpha. Okay, I'm sorry. So potential energy of a particle is proportional to, coordinate by equation x square minus 2x. So u of x is proportional to x square minus 2x. Okay, that's what they are saying. Will be equilibrium at. So this is simple.
Option
So
C.
since, yeah, maybe option C. Let's check. Okay, so for equilibrium, du by dx is equal to 0. That means d by du, sorry, d by dx of x square minus 2x is equal to 0. So derivative of this thing is 2x and derivative of this term is minus 2 only. Okay, because derivative of x is equal to 1. So 2x minus 2 is equal to 0, right? So x is equal to 1. Option C is the answer. Very good, Sanjay. A particle which is constrained to move along x-axis. Particle is constrained to move along x-axis, subjected to a force in the same direction, which varies with distance x of the particle from origin as this. Okay, this is the function f of x equals to minus kx plus ax cube. Okay, here k and a are positive constants. For x greater than 0, the functional form of potential energy u of x of the particle is. This is the question. Okay, what is the functional form of the potential energy u of x? So what do we need to do? Let's integrate this, right? So we know the relation between potential energy and the force, conservative force. So what's the relation? Integral of minus of f of x, okay, dx from 0 to x. Why 0 to x? Because we want the value of potential energy beyond 0. Okay, after 0, I mean, right? 0 and so for values of x which are greater than 0. So this is equal to potential energy at x minus potential energy at 0. Okay, so then let's substitute the values. Let's substitute f of x. So what do we get? It's integral from 0 to x of minus kx. We have this negative sign also, plus ax cube dx. Okay, and this is equal to this term. So we have two integrals here. So this minus minus becomes plus, k we can take out. So integral of x dx from 0 to x, and minus a I can take out. So integral from 0 to x of x cube dx, which is equal to, so this will become x square upon 2, right? Because lower limit is 0 only. Okay, so k times x square upon 2 minus, this will become what? X raised to 4 divided by 4. Okay, so minus a multiplied by x raised to 4 upon 4. So this is your potential energy function, right? This is the potential energy function. Okay, so put x equal to 0. What will you get? Okay, see, actually what we can find out it is, we can just find out this thing. Okay, we can just find out the difference in potential energy. We cannot find out potential energy. Okay, so we have to take some constant. We don't know what is potential energy at x equal to 0, but from this form what we can guess is what will happen when x will go on increasing. Okay, what will happen when x will go on increasing? So as x increases, what will happen? X raised to 2 will increase, but x raised to 4 will increase even more fast, right? Very, very fast compared to x raised to 2. Okay, so let's suppose, I'm sorry, let's suppose x is equal to 10. So x raised to 2 will be what? Will be 100. But x raised to 4 is what? It will be 10,000, right? Okay, and this is negative. This is negative. That means what will happen? The potential energy, the change in potential energy, okay, will go on decreasing. Decreasing meaning what? It is negative as x goes on increasing. Okay, so for higher and higher values of x, if you take the potential energy at that x, okay, so this is u, this is x. So for higher and higher value of x, if you take potential energy at that value of x, that is u of x, minus potential energy at 0. The potential energy at 0 will have some value. Okay, so for understanding, let's suppose it is 0. Okay, let's suppose, okay. So I'm not saying it will be 0. Let's suppose it's 0. You take some value. So if this value is above the x-axis, what will happen? The difference will be negative or positive. The difference will be positive, right? But if this value is below the x-axis, then difference will be positive or negative. The difference will be negative. And as we can see here, u of x minus u of 0. What's happening to this thing, u of x minus u of 0, as x increases? So this becomes more and more negative. Okay, so that means this graph will go down like this. So this is the answer. A conservative, it would be a force, right? A conservative force is given by F equals to K by R. When K is a positive constant, if the potential energy is 0 at R equals to R naught, find the expression for potential energy as a function of r. Okay, so this is given just like the last problem. What we will do is we'll take integral of f of c dr from r naught to some r, and this will give us what? It will give us potential energy at r minus potential energy at r naught, right? So minus of integral of conservative force from some initial to final value, it gives us potential energy at final value minus potential energy at the initial value. Okay, this we know, and they have given that the potential energy at r naught, it is 0. Okay, r equals to r naught is 0, so the second term is 0, right? So we get ur only on the right hand side. So this is what is that conservative force? It's k by r. So minus of integral from r naught to r of k by r. K you can take out because it's a constant. 1 upon r dr. And what is integral of 1 upon r? It is log r, right? It is log r. Everybody knows this.
Yes, sir.
Okay, so integral of this is log of r. Lower limit is r naught, upper limit is r, and you have minus of k, so u of r. Then substitute the upper and lower limit, so it is log of r minus log of r naught. Okay, so minus of k multiplied by log of r minus log of r naught, this is equal to u of r. Or you can say, if you multiply with this negative sign, it is log of r naught minus log of r, if you take negative sign inside. Okay, so log of r naught minus log of r, so log a minus log b equals to log of a by b, right? Because all options are given like this. Okay, so it will be k times log of, so they have given minus k times. Okay, so let's keep negative sign outside only, right? So u of r is equal to minus k times log of r upon r naught. This is the answer. Okay, so option B is the answer. This is clear? All right. Next question. A particle in a region of, a particle in a certain conservative force field has a potential energy given by U equals to this thing. The force exerted on it is. So this is again a straightforward question. So we know that F equals to minus of derivative of U with respect to what? So now here we have three coordinates. Okay, so x, y, and z, right? So we have to take three components of force. So remember the full formula. So it is minus of partial derivative of u with respect to x multiplied by I cap plus partial derivative of u with respect to y multiplied by j cap plus partial derivative of u with respect to z multiplied by k cap, right? This is the full formula. Oh, what's happening? Anyways, you can see this, no? Yes. So then let's substitute the value of u. So minus
Option
of,
C.
you got this? Okay, let's check. Very good. So partial derivative of u, which is 20 xy upon z. So 20 we can take out. Okay, 20 we will keep out. Or yeah, so let's keep out. Minus 20. So xy upon z. Okay, plus partial derivative of xy upon z with respect to y plus partial derivative of xy upon z with respect to z. Okay, and this multiplied by I cap, this multiplied by j cap, this multiplied by k cap. Okay, so what's the rule of taking partial derivative? You will treat other terms as constants. Okay, so oh, my mistake, I wrote z here. Okay, so when you take partial derivative with respect to x, you will treat y and z as constant. So these are constant. Okay, so it is minus 20 times. These are constants. What is derivative of x with respect to x? It's 1. Okay, so what is derivative of this term then? So y and z you can take outside, y upon z only. Okay, so it is y upon z times I cap plus, when you take partial derivative with respect to y, you will treat x and z as constants. So take them out, x upon z out multiplied by j cap, because derivative of y with respect to y is 1. And next you have derivative of this thing with respect to z. So x and y are constant, you can take them out. Derivative of 1 upon z is minus 1 upon z square, right? It is minus 1 upon z square. So it is minus xy divided by z square, okay, multiplied by k cap, right? So this is the answer. So which option did you say, Sanjay?
Option C, I say, sir. But option B
Okay,
is correct.
yeah, it is option B, because we have this extra negative sign, no? So it is option B, right? Because this minus and minus will become plus. Okay, so this is the answer, option B. Everybody? So after that, we'll see the work energy theorem. Okay, for constant force, all right. So we'll find out the work done by a constant force. Okay, so you know this formula, third kinematic equation of motion. What is that? V square minus u square equals to 2 times a into s. Okay, and you can move that 2 on the other side. So what I will do is I will multiply this equation with m, the mass. Okay, so I can write this equation as a multiplied by s is equal to half of v square minus half of u square. So what I have done is I have just taken this 2 on left hand side. So v square upon 2 minus u square upon 2 I will get. Okay, then I will multiply this equation with mass m. Okay, so left hand side, right hand side, I will multiply by mass m. So what do I get? I get m into a. What is that? Force, right? If force is constant and mass is not changing, then we can write force as mass multiplied by acceleration. Okay, so this is a force times displacement if we consider one-dimensional problem. Okay, so it is force times displacement. It's equal to, what do we get? It is half of m into v square minus half of m into u square. Okay, what is force times displacement? It is work, and that work is equal to half of mv square minus half of mu square, right? Half of m times final velocity square, okay, minus half of m times initial velocity square. So half of m times velocity square, this quantity is known as kinetic energy. Okay, we have been using this formula since 9th standard. Okay, so this is final kinetic energy minus the initial kinetic energy. Okay, and this is the work energy theorem. What is work done? What is work energy theorem? It says that work done by a constant force on an object changes the kinetic energy of object. So that work done is equal to the final kinetic energy minus the initial kinetic energy. So is it clear? All right. So let's come back to the topic. So for a variable force. So now, if you consider a variable force, let's consider one-dimensional thing again. So for one dimension, the work done by a force is F dot dx for small displacement. And if you want work done, okay, from some initial point to some final point, okay. So work done from initial point, let's say xi, to final point xf, okay. It will be the integral of f dot dx, right? So okay, so let me write this. So for a variable force, work done for small displacement, and we'll consider only one dimensional force. Work done for a small displacement is f dot dx only. And if I want net work done, okay, so let's suppose this is dw, small work done for small displacement dx. So net work done from some initial position xi, final position xf. So net work done will be equal to what? It will be integral of dw, that is integral of f dot dx from xi, initial position, to final position xf, and this is equal to integral from xi to xf of force can be written as mass times acceleration, and the acceleration can be written as dv by dt, right? So from xi to xf, this is m multiplied by dv by dt times dx. So now next thing what I will do is I will change the parameter. Okay, that means I will change the variable. So right now my variable is x. I want to change it to v. Okay, so what I will do is I can write this term as, okay, so you can move that dt in the denominator of dx, right? Okay, so that's not what we are doing. We can write it as a differential. Okay, so this can be written as what? Dx by dt times dv. Okay, so I'm changing the coordinate, sorry, I'm changing the parameter from x to v. So I will write this as this dt here. So this will become dx by dt. Okay, so dx by dt times dv. And at xi, suppose the initial velocity is u, and at final position xf, the velocity is v. Okay, so you get m times dx by dt into dv from initial velocity u to final velocity v. And what is this thing? Dx by dt, it's velocity, right? So u to v, m multiplied by v dv. M you can take out, and integral of this term v dv will be v square divided by 2. Okay, so you get work done by variable force also. You take m out, so it is v square upon 2 from initial value to final value. So from u to v, and that is equal to, if you substitute upper limit, it's v, lower limit is u. So it is v square divided by 2 minus u square upon 2, or you can write it as half of m into v square minus half of m into u square. Right? So you get the same formula. So work done is equal to what? Work done by a variable force also, it is equal to final kinetic energy minus the initial kinetic energy. So this thing is clear.
Yes, sir.
Ravindran? All right. So this is work energy theorem. Work done by a force is equal to what? The change in kinetic energy of an object, okay, on which that force is acting. Right? So let us discuss some problems. Sorry. Let us discuss some problems based upon this. A body of mass 3 kg is under a constant force which causes a displacement s in meters in it, given by relation s is equal to 1 by 3 t square, where t is in seconds. So work done by the force in 2 seconds is, okay. So now you are given with the displacement and t is in seconds. The work done in 2 seconds is, so s is equal to 1 by 3 t square, okay. Force is constant force, and we know work done is equal to what? Change in kinetic energy, right? Work done is equal to what? Change in kinetic energy. So I can take derivative of this. So what will be ds by dt? That's velocity, right? And what will be that? It will be 2 times t divided by 3, right? Derivative of this thing, derivative of t square is 2t, and you have this 3 in denominator, okay. So v is equal to this thing, and therefore you can say the work done is equal to final kinetic energy minus initial kinetic energy, or kinetic energy at t equals to 2 seconds minus kinetic energy at t equals to 0. Okay, so this is uh, what will be kinetic energy? Half of m multiplied by v square. What is velocity at t equals to 0? It's 0, right? So u is equal to 2 times 0 divided by 3, that is 0, right? Okay, and at t equals to 2, what will be its velocity? So it is 2 times 2 divided by 3. Okay, that is 4 upon 3. So take 4 upon 3 square, or here I will put 0. Here it is 2 times t divided by 3 square, right? So it is half of m multiplied by 4 times t square divided by 3, and you can cancel out this 4 by 2, so 2 will remain there, and now we can substitute values. So mass is 3, t is 2, okay. So it is 3 multiplied by t square, which is 2 square, so that's 4 times 2. 4 times 2 is how much? 8, okay. And this 3 and 3 will get cancelled because mass is equal to 3. Oh no, I have to take square of this thing also, no? Sorry. Okay, it will be 9 here. Okay, 3 square. So mass is 3. Okay, so you will have 8 divided by 3. Okay, 8 divided by 3 will be the answer,
Yes, sir.
right?
Yes, sir.
Okay, I had done a mistake here. Okay, anyways, so I didn't take square of this thing, 3. All right, so this is clear to everybody. Okay, so this is how we can use the work energy theorem. Okay, let's discuss next problem, which is similar. A force acts on 3-gram particle in such a way that the position of the particle as a function of time is given by this thing, where x is in meters, e is in seconds. Okay, the work done during first 4 seconds is, so find out velocity, right? X is given 3t minus 4t square plus t cube. Find out velocity. So dx by dt is what? So 3 minus derivative of this will be what? 2 times t multiplied by 4. So it is 8t plus derivative of this thing is 3t square. 3t square. Okay. So this is velocity, right? So let's suppose initial velocity is u. How much is u? Put t equals to 0. So this term will be 0. This term will become 0. So u is equal to 3 meters per second. And the velocity at 4 seconds is suppose v. Okay, so v is at t equals to 4. How much is that? So 8 times 4 is 32. And this is what? T square. So 16 times 3 is 48. 48 minus 32. How much? 16. 16 plus 3. How much? 19. Right? 19 meters per second. Okay. And then what will be the work done? Work done is equal to final kinetic energy minus initial kinetic energy. Okay. So let's take m by 2 out. M by 2 v square minus u square. What is m? 3 grams. So 3 multiplied by 10 raised to minus 3 divided by 2. 19 square. What is 19 square? So see, we can use trick like this. Okay, this would be difficult, multiplying 19 with 19. So what you do is multiply 19 with 20 minus 1. Okay, so this thing is, so ultimately what you are doing, you are finding 19 square. So 19 times, okay, because 20 minus 1 is 19. 19 times 19. Okay, so 19 times 20 is 380 minus 19 times 1 is 19. Okay, so that's how you can find out squares. Okay, if you don't know. All right, so 361 minus u square. How much is u? It is 3. 3 square is 9. Okay, so 361 minus 9 is how much? 353. Sorry, 352. Okay, 352. 352 divided by this 2. So it is 352 divided by 2. Will be how much? 176. 176 multiplied by 3. 528. This is answer. 530. Option D is the answer. Right? If my calculations are
Yes,
correct.
sir.
Yes, sir.
Okay, Ravindran. All right. So 528 multiplied by 10 raised to minus 3 is 528 millijoules. And closest one is 530. So this is the answer. Right. All right. Let's move on to the next problem. The kinetic energy acquired by mass m in traveling distance d starting from rest under the action of a constant force is directly proportional to kinetic energy acquired by a mass m in traveling distance d starting from rest under the action of constant force. Okay, so force is constant. What is the kinetic energy acquired? So they are saying it is starting from rest. Okay, so we know the final kinetic energy minus initial kinetic energy is equal to the work done. This is work energy theorem. Okay, and it is starting from rest. So initial kinetic energy is 0. Final kinetic energy is equal to work done by a constant force. So what will be that constant force? Sorry, what will be the work done by constant force? Force multiplied by displacement. It is force times displacement. Okay, so force is constant, displacement is given, it's d. So does it depend on mass? Yes, no?
Yes, sir.
Is it depending on mass? Tell me. Kinetic energy of any object, okay, which you are pushing, let's suppose with a constant force in same direction, it is equal to F times d, force times displacement. Okay, so it doesn't depend on mass, it is F times d. It depends on force and the displacement only. What will depend on mass? See, kinetic energy is half of m into v square. So what will happen? If mass is less, speed will be more. If mass is more, speed will be less. But the kinetic energy that you are giving, okay, by pushing that object with constant speed, it will be same. It does not depend on mass. Got it? Yes, no? Option B is the answer.
Yes, sir.
Yes, sir.
Okay, is there a confusion? They are not
Clear, sir.
asking you the, yeah, they are not asking you the formula for kinetic energy. Okay, so kinetic energy is half of mv square. It will depend on mass, right? If you take the formula for kinetic energy. So under this scenario, what's happening? You are pushing that object from rest, starting from rest. So you are applying a constant force F. Okay, let's suppose of 100 Newton, and the displacement is 10 meters. So how much would be the kinetic energy? 100 times 10. So have we considered a mass here? Whatever is the mass, let's suppose the force is 100 newtons, displacement is 10. So how much would be the kinetic energy if you push that object starting from rest with a force of 100 newton and you give displacement equal to 10? So it will be 1000 joules. Okay, doesn't matter how much is the mass. If mass is less, velocity will be more. If mass is more, velocity will be less. Okay, this product of half of mv square will be equal to what? 1000 joules. So it does not depend on the mass. Clear now? If there is any confusion.
Yes, sir.
Yes, sir.
Yes, Ravindran? Okay, good. Then let's see the next question. A particle of mass m at rest is acted upon by a force P for time t. Kinetic energy after an interval t is. So this is the question. Okay. So it is acted upon by a force P. P is the force. Okay. So now, so can you find out momentum? It is starting from rest. Okay. So momentum, and I will take small p for that. It's equal to mass times velocity, and its initial momentum will be 0, right? Okay, initial momentum will be 0. So what will be momentum? Final momentum? See, this P will be equal to, force is equal to final momentum mv minus initial momentum, which is 0, divided by T. So final momentum, okay, mv is equal to what? P times T, right? And therefore, now you want, okay, kinetic energy, which is half of m into v square, which is equal to, you can say this half of, I can write this as m square v square divided by m, or p square upon 2m, right? Which p? The small p, which is momentum. And that is mv square can be written as p square t square, right? P square t square divided by 2m. So this will be the answer, right? Option B is the answer.
Yes, sir.
Others?
Yes, sir.
Ravindran? Oh, you already said clear. Ravindran, can't you speak? All right. Let's move on to the next problem. The rate of decrease of kinetic energy is 9.6 joules per second. Find the magnitude of force acting on particle when its speed is 3 meters per second. Okay, so what is given? The rate of decrease in kinetic energy is given. Okay, no problem. So the rate of decrease in kinetic energy, this is given. So derivative of kinetic energy with respect to time, this is given. Okay, and find the magnitude of force, this is the question. All right, so can we write F times dx for small displacement? F times dx is equal to change in kinetic energy, because work done is equal to what? Change
Yes,
in,
sir.
right? So work done is equal to change in kinetic energy. So for small displacement, I can write this is equal to dk. Okay, and then you are given with dk by dt. So I can write this as, I mean, I'm dividing by dt on both sides. So dk by dt is f times dx by dt. And what is dx by dt? It is v. Okay, and what do you want? You want force only. So take v on other side. So you get force is equal to 1 upon v multiplied by dk by dt. So dk by dt is given, right? V is given. Okay, and you got the force then. Okay, so it is 9.6 divided by v, dk by dt is 9.6 divided by v is 3. So 3 3s are 9, 3.2. 3.2, yes, option A. So 3.2 newtons is the answer. Is it clear?
Yes, sir.
Yes, sir.
Okay, good. Let's, oh, there is no next question.